Let's now set up images and image information that we will use to train a YOLO version 3 convolutional neural network based on the 2014 COCO dataset. First, a few notes. I have discovered through experience that training YOLO version 3 convolutional neural networks using darknet succeeds when each image file is a JPEG file. I've discovered that training YOLOv3 CNNs succeeds when each image file has a corresponding label text file with the same prefix. Each line in each label file corresponds to one bounding box around an object in the appropriate image. Each line contains 5 data points that are separated by whitespace characters, and each line ends with a new line character. The 5 data points record the index of the class name of the object in a list of class names of objects associated with the COCO dataset, the ratio of the horizontal center of the bounding box to the width of the image, the ratio of the vertical center of the bounding box to the height of the image, the ratio of the width of the bounding box to the width of the image, and the ratio of the height of the bounding box to the height of the image. I have discovered that training YOLOv3 CNNs using darknet and a custom dataset succeeds when training images and label files are in the same directory. However, I've discovered that the images and label files associated with the COCO dataset and images and label files associated with the Pascal VOC 2007 and 2012 datasets are organized differently. Let's explore downloading, unzipping, and organizing images and label files associated with the COCO dataset first. Then, creating a text file listing of paths to training images, and creating a text file listing of paths to validation/development images. We are still in the root content darknet directory. I changed directory into the root content darknet data folder by executing the command $cd data. I create the folder root content darknet data COCO by executing the command make dir COCO. So here we are in root content darknet, going to the data folder and going to the COCO folder, which is empty because we just made it. I changed directory then into the COCO folder by executing the command cd COCO. I create the folder root content darknet data COCO images by executing the command make directory images. Now in our COCO folder, we have our images subfolder. I'm going to change directory into the root content darknet data COCO images folder by executing the command $cd images. I will download to our present folder the zipped folder of 2014 COCO training images by executing the command wget. The C option corresponds to continue, and the URL to the 2014 COCO training dataset. Oops. http://images.cocodataset.org/zip files/train2014.zip. The continue option allows wget to resume downloading train 2014.zip in a case of communication with the COCO dataset.org server failing. All right, so the Google server is downloading the Train 14 2014 COCO training images at 37 megabytes per second. And it still seems like it will take 6 minutes. And just throwing that in, let's say 6 minutes times 60 seconds per minute times 37 megabytes per second. So we're looking at 13.3 gigabytes worth of images associated with the 2014 COCO training dataset. See you in a few. I'm back. We've successfully downloaded our 2014 COCO training images into the zipped folder, root content darknet data COCO images, and train 2014.zip. This came from cocodataset.org. Let's unzip train 2014.zip into a folder of 2014 COCO training images using the command !unzip Q to suppress printing image file names, and the file to unzip. All right, it seems it took about a minute or two, which is pretty impressive, to unzip 13 or so gigabytes of 2014 COCO training images. Okay, I will download to our present folder, root content darknet data COCO images, the zipped folder of 2014 COCO validation / development images by executing the command wget continue images.cocodataset.org/zips/val2014.zip. Okay, here we are again, downloading at, say, 36.3 megabytes per second, and it's looking to be about 3 minutes long, so let us check this while we wait. So we have 3 minutes times 60 seconds per minute times 36.3 megabytes per second. So the 2014 COCO validation / development dataset contains 6.5 gigabytes worth of images. Google really downloads and processes very quickly. I hope to use Google Colaboratory to do my main training for all of my custom datasets, even though when I begin to modify the darknet deep learning framework using Visual Studio, I will do all of the architecture manipulations and forward propagation on a local PC with a GPU. But I will do my training using Google Colaboratory. Okay, I'm just checking. So it seems that the end size of the training 2014.zip folder was 12.6 gig, and the size of the 2014 validation dataset for COCO was 6.2 gig, so not too far off. Of course, the unpacked image folders will have a larger total sizes. All right, so now that we've successfully downloaded our 2014 COCO validation dataset images in a zipped folder from cocodataset.org, I will unzip val2014.zip into our folder of 2014 COCO validation images using the command !unzip, suppress listing the file names of the images and the relative path to our zipped folder, which is val2014.zip. All right. After unpacking the 2014 COCO training and validation images to the train 2014 and val 2014 folders in root, content, darknet, COCO images, I will return to root, content, darknet, data, COCO by executing the command %cd ... I will download to our present folder labels.tjz, which is an archive of 2 folders of label files corresponding to the 2014 COCO training and validation images. I will execute the command wget continue https://pjready.com/media/files/labels.tjz. Interesting. It seems that that website was not found. !wget option continue https://pjready.com/media/files. Got the COCO subdirectory in there. /labels.tjz. Moving fast. For a total of only 17.2 megabytes. Very fast. Let's unpack into root, content, darknet, data, COCO this archive labels.tjz. This new labels folder that will be created will contain 2 folders of label files corresponding to the 2014 COCO training and validation images. Let's execute the command !tar corresponding to unpacking tape archive files. Option X corresponding to let's do an extraction. Option Z, which indicates that it is a TJZ file or a tape archive.gzip file. And option F, which indicates that the archive that we are unpacking is a file as opposed to, say, an external drive. And now we need to reference the labels archive that we are unpacking. All right. So here in the root content darknet data COCO folder, we have a labels folder containing a train 2014 and a val 2014 folder of label files corresponding to all of the 2014 COCO training and validation images. I'm still in the root content darknet data COCO directory. I will create a list of the file names of all of the 2014 COCO training images by executing the Python code import operating system library, list of training image file names equals the output of list all of the files in the directory, root content darknet data COCO images train 2014. I will print the number of 2014 COCO training images and a short sublist of file names of 2014 COCO training images by executing the Python code print number of 2014 COCO training images and the string form of the length of the list of training image file names. And a new line character just for prettifying the output of this code cell. Let's also print the first 5 file names of 2014 COCO training images. All right, let's try that out. Cool. So the number of 2014 COCO training images is 82,783. That's a lot. And here's a small sublist of the file names of the 2014 COCO training images. Let's now create a list of the names of files containing labels for our 2014 COCO training images by executing the Python code list of names of files containing labels for training images equals the output of the function list all of the files in directory root content darknet data COCO labels train 2014. I will print the number of files containing labels for 2014 COCO training images and a short sublist of the names of files containing labels for training images. By executing the Python code, print number of files containing labels for 2014 COCO training images and print the string form of the length of the list of names of files containing labels for training images. And print a new line character just to prettify the output of this code cell. Additionally, let's print the first 5 names of files containing labels for 2014 COCO training images. Try that out. All right. So the number of files containing labels for 2014 COCO training images is 82,081. And here are the first 5 names of files containing labels for 2014 COCO training images. Unfortunately, the number of files containing labels for training images is significantly smaller than the number of training images. When we construct our text file listing of paths to training images, we will have to be careful to only include paths to training images with corresponding label files. More on this later. Given that I am focused on efficiently training a YOLO version 3 convolutional neural network on the COCO dataset, I will follow Joseph Chet Redman's example and will lump most of the 2014 COCO validation dataset into my actual training dataset. My actual training dataset will contain many more images and label files than the original 2014 COCO training dataset. To get started with the 2014 COCO validation dataset, I will create a list of file names of all of the 2014 COCO validation images by executing the Python code list of validation image file names equals the output of the function list all the files in directory root content darknet data COCO images val 2014. I will print the number of 2014 COCO validation images and a short sublist of file names of 2014 COCO validation images by executing the Python code print number of 2014 COCO validation images, the string form of the length of the list of validation image file names, and a new line character to prettify the output of this code cell. I will also print the first 5 file names of 2014 COCO validation images. Trying that. All right. So the number of 2014 COCO validation images is 40,504. And here are a few examples of file names of the 2014 COCO validation images. Next, I will create a list of the names of files containing labels for our 2014 COCO validation images by executing the Python code list of names of files containing labels for validation images is the output of the list all files in directory function, list all files in the directory root content darknet data COCO labels val 2014. I will print the number of files containing labels for 2014 COCO validation images and a short sublist of the names of files containing labels for validation images by executing the Python code print number of files containing labels for 2014 COCO validation images, the string form of the length of the list of names of files containing labels for validation images. And a new line character to printify the output of this code cell. Additionally, I will print out the first 5 names of files containing labels for 2014 COCO validation images. Let's try that. All right, it didn't like the extra space I put after this separation of parts of a printed string. Okay, so the number of files containing labels for 2014 COCO validation images is 40,137, and here are a few file names for label files corresponding to 2014 COCO validation images. Unfortunately, the number of files containing labels for validation images is significantly smaller than the number of validation images. When we construct our text file listing of paths to training images, which will include most of our validation images, we will have to be careful to only include paths to training images from the validation dataset with corresponding label files. Now, I'm going to create storage for a complete master list of file names of images in both the original 2014 COCO training dataset and the original 2014 COCO validation dataset. All of the image file names that go into this master list will have corresponding label files. To create this storage for this master list of image file names, I'm going to execute the Python code list of image file names is an empty list. Now, I want to let you know about an assumption that I'm going to make. The assumption is that every label file has a corresponding image file. It turns out to be true, but it's still an assumption at this point. Assuming that every label file has a corresponding image file, let's fill in our master list of image file names by iterating through each list of label file names and adding the file name of the corresponding image to the master list of image file names. Just in case every label file does not have a corresponding image file name, I will check to see if the image file name corresponding to each label file is actually in the appropriate list of image file names. To do all of this, let's execute the following Python code. For name of file containing labels for a training image in the list of names of files containing labels for training images, the corresponding image file name equals the prefix of the name of the file containing labels for this training image plus the suffix, the file extension. If the corresponding image file name to the chosen labels file name is in the appropriate list of image file names. We're dealing with training right now. Let's append to the master list of image file names the absolute path of the image file name that we've come up with. Let's do the same thing for all of the labels associated with validation images. So, for name of file containing labels for a validation image in the list of names of files containing labels for validation images. Let's create the corresponding image file name as the name of the file containing labels for the present validation image, the prefix of this name specifically, and the suffix, the file extension for the image. If the image file name corresponding to our present label file name corresponding to a validation image, hopefully, is in the list of validation image file names, append to the master list of image file names the absolute path these forward slashes are really important. Append to the master list of image file names the image file name that we've come up with based on our scan through the list of names of files containing labels for validation images. Let's try this out. Seems to be working. All right. I will check to see if every label file actually has a corresponding image file by executing the following Python code. If the length of the list, the master list, of image file names equals the sum of the length of the list of names of files containing labels for training images and the length of the list of names of files containing labels for validation images print yes. The length of the master list of image file names is equal to the sum of the lengths of all lists of label files. And indeed, yes, the length of the master list of image file names is equal to the sum of the lengths of all lists of label files. That means all label files have corresponding image file names. It also means that every image file name in the master list of image file names has a corresponding label file name. Next, we're going to work with that master list of image file names. As is common practice in training neural networks, I will randomize our master list of image file names to prepare to divvy up the absolute paths to image files into a text file listing of paths of images we actually want to use to train a YOLO version 3 convolutional neural network on the 2014 COCO dataset, and a text file listing of paths to extra images that we could hypothetically use for validating how well our YOLOv3 CNN trained, and or how useful we can expect our network to be. I will randomize our master list of image file names by executing the Python code import the random library, create the randomized list of image file names as a hard copy of the master list of image file names, and then shuffle in place the randomized list of image file names. Finally, I will create our text file listing of paths to images we actually want to use to train a YOLO version 3 convolutional neural network on the 2014 COCO dataset. I will also create our text file listing of paths to images we actually want to use for validation. I will do these things by executing the Python code. Number of validation images equals 5,000. Number of training images equals the length of our master list of image file names minus our specified number of validation images. I will open the file trainval no5k.txt for writing, and this lives in root content darknet data COCO. For each index between 0 inclusive and number of training images minus 1 exclusive, write to file the entry in randomized list of image file names, the entry corresponding to the present index, and then write a new line character. then write the entry in randomized list of image file names corresponding to the number of training images index, or number of training images -1. Similarly, let's open 5k.text for writing as our text file listing of paths to our validation images. For each index between 0 inclusive and number of validation images -1 exclusive, let's write to 5k.text the entry in randomized list of image file names corresponding to the index number of training images plus I, or the number of training images plus I plus 1 index in randomized list of image file names. And then let's add a new line character. And then let's write the very last entry in randomized list of image file names to our text file listing of absolute paths to validation images. Let's try that out. Okay, here I forgot an in. Try again. Here I shortened randomized list of image file names, so I need to fix that. That seemed to work. All right. Okay, so now that we've created our text file listing of absolute paths to our training images and our text file listing of absolute paths to our validation images, let's check to see whether we have divvied up all of our absolute paths in randomized list of image file names to the two text file listings. So let's open again train val no 5k, this time for reading, and let's print the number of absolute paths in our text file listing of paths to our training images. And then let's actually print this number, which is the length of the list of lines in train val no 5k.text. Similarly, let's print the number of absolute paths in our text file listing of paths to our validation images by opening 5k.text for reading and printing then the length of the list of lines in 5k.text. See if this works. All right, it seemed to work. And indeed, we have 117,218 absolute paths to training images, our training images, as opposed to the original training images. And we have 5,000 absolute paths to our validation images, as opposed to the original validation images. And this total is the total number of label files with corresponding images or image files with corresponding labels in the in the COCO 2014 training and validation datasets. We are now ready to execute our darknet binary, configured to train a YOLO version 3 convolutional neural network on the 2014 COCO dataset. Before we do, though, let's set up the Pascal VOC 2007 and 2012 datasets, and a text file listing of paths to training images associated with the Pascal VOC 2007 and 2012 datasets. To do this, let's reset back to our root content darknet directory by executing the command $cd ... twice. Let's explore downloading, unzipping, and organizing images and label files associated with the Pascal VOC 2007 and 2012 datasets, and creating a text file listing of paths to training images. I've gone ahead and scrolled down a little bit within our Jupyter notebook and returned to view our root content darknet folder in our file explorer. We are still in the root content darknet directory. I create the folder root content darknet VOC data from 2007 to 2012 by executing the command make directory VOC data from 2007 to 2012. I change directory into this new folder by executing the command $cd VOC data from 2007 to 2012. I download to our present folder tape archive files containing images and image information associated with the Pascal VOC 2012 training and validation datasets, and images and image information associated with the Pascal VOC 2007 training and validation datasets by executing the commands wget https://pjready.com/media/files/voc train val _11-may-2012.tar and wget https://pjready.com/media/files/voc train val _6 November 2007.tar. Here we have about 2 minutes of download, 60 seconds per minute, let's say 21 megabytes per second. So we're looking at about 2.5 gigabytes worth of Pascal VOC 2012 training and validation data. and I'm not sure what the size of the 2007 archive will be yet. Okay, it turns out that the tape archive file corresponding to the VOC 2012 dataset is only 1.8 gigabytes. Interestingly, the tape archive file corresponding to the VOC 2007 training and validation datasets is only about 440 megabytes. All right, so then going into our root content darknet VOC data folder, here we have the downloaded archives with the 2007 and 2012 training and validation datasets. I will unpack into root content darknet our VOC data folder, a VOC 2012 folder containing images and image information associated with the Pascal VOC 2012 data and validation datasets. By executing the command !tar, option X for extract, option F to reference that we are extracting a file, and the relative path of the 2012 archive. So here in the newly created VOC DevKit folder is a VOC 2012 folder, which contains a folder of JPEG images and a folder of information on each of those JPEG images. Each of these annotation files are in an XML encoding. So similarly, let's unpack into a VOC 2007 folder the Pascal VOC 2007 training and validation datasets by executing the command !tar, X for extract, F for reference to a file, and then the relative path to the 2007 datasets archive. All right, that's done. Here is the VOC 2007 folder with a JPEG images folder containing the VOC 2007 training and validation images, and an annotations folder encoding information about each image in an XML format. All right. Given that this VOC dev kit folder does not contain label files for any images that we will use to train a YOLO version 3 convolutional neural network on the Pascal VOC 2007 and 2012 datasets, let's write a Python script to create folders of label files for all images associated with Pascal VOC 2007 and 2012 training and validation datasets. These labels folders will live in the VOC 2007 and VOC 2012 folders. Each image used for training will have an associated labels file. Each line in each label file will encode information on one object/bounding box identified within the corresponding image. Each line will contain the index of the class name of the object. The index references a list of class names associated with the Pascal VOC 2007 and 2012 datasets. This index will be followed by a whitespace character, which will be followed by the ratio of the horizontal position of the center of the bounding box to the width of the image, followed by a whitespace character, followed by the ratio of the vertical position of the center of the bounding box to the height of the image, followed by a whitespace character, followed by the ratio of the width of the bounding box to the width of the image, followed by a whitespace character, followed by the ratio of the height of the bounding box to the height of the image, and followed lastly by a new line character. In order to create these folders of label files in these two folders, let's import the Python operating system library if we haven't already. In order to access image information encoded in XML files, let's import the Python xml.etree.element3 library as ET. In order to enter indices representing class names into our label files, let's create a list of all 20 class names associated with the Pascal VOC 2007 and 2012 datasets by writing classes equals airplane, bicycle, bird, boat, bottle, bus, car, cat, chair, cow, dining table, dog, horse, motorbike, person, potted plant, sheep, sofa, train, TV monitor, and that's it. That's quite a list of classes. Triads, excuse me. To access each of 4 text file listings of paths to Pascal VOC 2007 and 2012 training and validation images that we can then use to find image information files that we can then use to fill in label files, let's define a list of tuples representing the Pascal VOC 2012 training dataset, the Pascal VOC 2012 validation dataset, the Pascal VOC 2007 training dataset, and the Pascal VOC 2007 validation dataset. That's right. Datasets equals a list of tuples, the first tuple being 2012 training, second tuple 2012 val, third tuple 2007 train, and the fourth and last tuple 2007 val. All right. The 4 text file listings of paths to Pascal VOC 2007 and 2012 training and validation images, represented by these 4 tuples, are train.txt and val.txt in each of these 2 folders, a few levels down. So let's go into one of these folders, VOC 2012, and into the image sets folder and into the main folder, and scroll all the way down, and we see val.txt here and train.txt here. Similarly, in the VOC 2007 folder, in the image sets folder, in the main folder, there is a val.txt and a train.txt. Okay, so now we're in view of the darknet directory again. All right, so let's actually create folders for our label files by writing os.makeDirs VOC devkit VOC 2012, the labels folder. And let's make a directory for labels folder associated with the 2007 dataset. This labels folder will contain all of the labels for all of the images associated with the Pascal VOC 2007 training and validation images. Okay. To prepare to create all of our label files, let's first set up a for loop to allow us to use each of our 4 text file listings of Pascal VOC 2007 and 2012 training and validation images by writing for year and dataset in datasets. For each year and dataset, let's create a list of image prefixes based on the text file listing dataset.txt by writing with open VOC devkit /VOC plus year plus /image sets /main plus dataset plus .text. We are reading, say, train.txt in the 2012 folder, and let's call this file object we are opening text file listing. And let's create our list of image prefixes associated with the present year and dataset by accessing our text file listing object, reading its contents into a string, stripping the new line character from the end of each line, and padding each line with whitespace characters, and then splitting by whitespace character. To further prepare to create all of our label files, let's set up a nested for loop to allow us to execute the same label file creation code for each image prefix. We will write for each image prefix in list of image prefixes. For each image prefix, let's create and open the label file, root content darknet VOC data, VOC devkit, VOC year, the labels folder corresponding to that year, and the image prefix.txt file within that labels folder corresponding to that year. Let's open this image prefix.txt file for writing by writing with open VOC devkit / VOC plus year plus / labels / plus image prefix plus .text. Open this file for writing and call the file object label file. All right, while our label file is open for writing, let's open the corresponding image information, which I'll call an annotation file, also for reading by writing, with open VOC devkit / VOC plus year plus / annotations plus image prefix plus .xml open for reading. Call this file object annotation file. While our annotation file is open for reading, let's parse the annotation file into an XML tree by writing tree equals element tree dot parse annotation file object. Let's save the root annotation object defined in the annotation file to the variable root. Let's save root size to the size branch variable. Let's save size branch's width object to image width. Let's save size branch's height object to image height. For each object with tag object in the root object, let's save this object to object branch. Then Let's save this object's name to object class name. Let's decide whether this object is a difficult object to identify as a member of the object's class. If the object's class name is actually in the list of classes associated with the Pascal VOC 2007 and 2012 datasets, and the image is not too difficult to identify as a member of the object's class, then let's save the index of the object's class name in our list of classes to index of object class name in list of classes. Let's now calculate the ratio of the horizontal position of the center of our bounding box / object to the image width. All right, now that we have the ratio of the horizontal position of center of bounding box / object to image width, let's calculate the ratio of vertical position of center of our bounding box / object to the image height. First, I would like to say that I adjusted this equation, defining the ratio of the horizontal position of the center of the bounding box / object to image width, by changing up the denominator to be the image width. And here now I have the ratio of the vertical position of the center of the present bounding box to the image height. And let's now calculate the ratio of the bounding box width to the image width. Finally, let's calculate the bounding box height ratio to image height. All right, so now for each object in our image, if the object class name in our XML annotation file is in the list of classes associated with the Pascal 2007 and 2012 datasets, and it's not too difficult to identify this object as a member of its class, fill in the present labels file for the present image with the index of the object class name in our list of classes associated with the Pascal 2007 and 2012 datasets. Define the ratio of the horizontal position of the center of the bounding box / object to the image width. Define the ratio of the vertical position of the center of the bounding box / image to the image height. Define the ratio of the bounding box width to the image width, and define the ratio of the bounding box height to the image height. And finally, let's write to our present label file a string containing the index of the object's class name in our list of classes first. And this will be writing to our label file. So I can say label file dot write the index of the object class name in our list of classes, plus a white space character, plus the ratio of the horizontal position of the center of the bounding box / object to the image width, plus a white space character, plus the ratio of the vertical position of the center of the bounding box / object to the image height, plus a white space character, plus the ratio of the bounding box width to the image width, plus a white space character, plus the ratio of the bounding box height to the image height, plus a new line character. All right. Now that we've created all of our label files, or are about to, let's execute this first. All right, first error. Right now, these are integers, not strings, or floats, not strings. So let's convert all of these numbers to strings. Okay. So I'm going to remove these labels folders that were probably created during our first run that ended up with an error by writing remove VOC devkit / VOC 2012 / labels. All right, and doing the same for the 2007 datasets. Okay, that gives us a fresh start with creating these labels directories for all of our labels files. Let's try again. Seems to be working better this time. And it seems to have worked. Great. All right. Now that we've created all of our label files corresponding to all images in the Pascal VOC 2007 and 2012 training and validation datasets, let's create a text file listing of paths to images that we will actually use to train a YOLO version 3 convolutional neural network on the Pascal VOC 2007 and 2012 datasets. So, for each year and dataset in datasets, the list of tuples of years and datasets. Let's find again our list of image prefixes corresponding to this year and dataset with open VOC devkit / VOC plus year plus / image sets / main. Whoopsie-doo. Plus dataset plus .text. Open this as a file to read. Call it text file listing. Define our list of image prefixes associated with this year and dataset as text file listing read to a string, strip new line characters and pad with white space, split and remove white space. All right. And then let's open for writing a text file listing of absolute paths to images associated with this year in dataset. And open this for writing, call it text file listing of paths to images. This will be saved in this VOC data from 2007 to 2012 folder. For each image prefix in our list of image prefixes, let's write to our text file listing of paths to images the absolute path of the present image, which corresponds of the current absolute working directory, plus VOC dev kit /VOC plus year plus JPEG images plus image prefix plus the image file extension plus a new line character. Let's try that. Seemed to work. And here are 4 text file listings of absolute paths to associated images with this dataset. And now that we have 4 text file listings of absolute paths to images associated with specific years and datasets, I execute the following command to concatenate these listings into one text file listing of paths to images that I actually want to use to train a YOLO version 3 convolutional neural network on the Pascal VOC 2007 and 2012 datasets. I execute the command !cat 2007 train.text, 2007 val.text, 2012 train.text, and 2012 val.text into just a general train.text text file listing of absolute paths to training images that I will actually use to train a YOLO version 3 convolutional neural network on the Pascal VOC 2007 and 2012 datasets. All right. To check that everything is ready for training, I will print the number of paths to images we actually want to use to train a YOLO version 3 CNN on the Pascal VOC 2007 and 2012 datasets, and a short sublist of the paths to actual training images by first executing the command, the Python code with our new text file listing of paths as a file object, print the length of the list of lines in this train.text file object. It is 16,551 paths to actual training images. And let's explore what each of the first 5 of these paths looks like. It's an absolute path starting at root content, darknet, VOC data, VOC dev kit, VOC 2007, JPEG images 0000 in front of all of the image file names, and then 2 digits and a file extension .jpeg. Looks great to me. As you can see, we have about 17,000 paths to actual training images, 16,551. Now we are ready to execute our darknet binary configured to train a YOLO version 3 convolutional neural network on the Pascal VOC 2007 and 2012 datasets. But before we do, let's set up a custom dataset and a text file listing of paths to training images associated with this custom dataset. Let's reset back to our root content darknet folder by executing the command $cd ... once. To extract to our root content darknet directory the folder Quercus dataset of training images of oak leaves and label files encoding the positions and sizes of bounding boxes in each image, from the zipped folder Quercus dataset.zip in my Google Drive's darknet folder, I navigate to the root content directory by executing the command $cd ... Then I execute the Python code import Python library zip file with zipped file Quercus dataset open for reading. Extract from zipped file Quercus dataset to the darknet folder on our virtual machine. A folder called Quercus dataset with 111 images containing oak leaves and 111 corresponding label files. I return to our darknet directory by executing the command $cd ... darknet. To create listings of images corresponding to training and validation datasets of images of oak leaves and Quercus, the genus of oak trees, I first execute the following Python code to find the number of images in Quercus dataset. If we haven't already, import the Python operating system library. Define number of images to be the length of a list of the files in the Quercus dataset folder divided by 2 because there are an equal number of images containing oak leaves and corresponding label files. I execute the following Python code to create an image file, label file, image file, label file, image file, label file list of all of the files in Quercus dataset. Each label file, of course, records the positions and sizes of bounding boxes in an image and has the same prefix as that image, and immediately follows that image file in my list. list of image and label files equals the list created by listing the contents of the Quarkus dataset directory. Sort the list of image and label files in alphabetical order from A to Z. I execute the following Python code to create a one-dimensional array of randomized image indices that can be used to create a randomized list of just image files. Let's import the NumPy Python library as np. Let's define a one-dimensional array from 0, 1, 2 to num images minus 3, num images minus 2, num images minus 1. Let's define our randomized array of image indices as a hard copy of the image indices array. And let's shuffle our initialized randomized indices array. I execute the following Python code to create a randomized list of image files. Creating storage for our randomized list of image files for index in our randomized image indices array. Append to what will be the randomized list of images the element of list of image and label files corresponding to 2 times that index. So in more English terms, for every even indexed file name in the list of image and label files, which would be the 0th, 2nd, 4th, 6th, 8th, etc. file names, which are the images. Add the image file name to our randomized list of images. Okay. Given that as of November 6th, 2019, there are 111 images in my dataset of Oakleaf images and label files, I define the number of images in my training dataset to be 100. I define the number of images in my validation dataset to be the difference between the number of images in my Oakleaf dataset as a whole and the number of images in my training dataset. I then write the first 100 images to root content darknet Quarkus dataset train.txt, and the remaining num validation images to root content darknet Quarkus data validate.txt. Dry eyes again. Okay. Num training images equals 100. Num, let's say validation images equals num images minus num training images. Change this. Okay. With file train.txt open for writing, for each index ranging from 0 to num training images minus 2, write to file train.txt the relative path to the root content darknet folder, Quarkus dataset plus the element in randomized list of images corresponding to our present index between 0 and num training images minus 2. And add a new line character. Finally, write to file train.txt the relative path to our darknet folder, Quarkus dataset plus the image file name in our randomized list of image files that is the last image file name in our randomized list. Okay, here I forgot indexing. Okay. Also, with file validate.txt open for writing, for each index between 0 and num validation images minus 2. Write to file validation.txt the relative path to root content darknet, that is Quarkus dataset plus the image file name in our randomized list of image files at our present index beyond the number of training images, -1. And finally, write to file validate.text the relative path to root content darknet, that is Quarkus dataset, plus the last image file name in our randomized list of image files. Okay. File validation.text not defined. Okay. It's actually validate.text corresponding to train.text. Let's try that. It worked. All right. So I verify that train.text and validate.text are randomized lists of paths to Quarkus dataset training and validation images. I will first check the lengths of train.text and validation.text because I ran my first writing to train.text twice given my errors in the above code cell. So let's open Quarkus dataset train.text for reading. And let's print the length of the list of lines in file train.text. Okay. There are only 100 training images paths in file train.text. So I think the with block successfully closed file train.text before it was reopened and rewritten. All right. So I'm going to actually check the length here of validate.text as well. No file Quarkus dataset /validate.text. Okay, let's check that. Darknet, Quarkus dataset. I named it validation.text. I'm going to go up here and change this to validate for the future, but then simply rename to validate.text here. Okay, rerunning this. There are 11 paths to validation images in root content darknet, Quarkus dataset, validate.text. Okay, I will print the first 5 lines to the Quarkus dataset training images to see if they are randomized and see if they're JPEG images, and just to take a look at the paths themselves. So print the first 5 paths to Quarkus dataset training images in root content darknet Quarkus dataset train.txt R, and let's print the first 5 lines of root content darknet Quarkus dataset train.txt. And here they are. These are relative paths now to root content darknet. It looks okay. Similarly, let's print the first 5 paths to Quarkus dataset validation images in root content darknet Quarkus dataset validate.txt R. And let's print out the first 5 lines of root content darknet Quarkus dataset validate.txt. And here are those. So everybody looks random. Everybody looks like a JPEG image. And the relative path names seem to be good. And I think the training can deal with relative path names as well as absolute path names, but we'll see. Okay. So we are ready to execute the darknet binary in our root content darknet folder to train a YOLO version 3 convolutional neural network on the 2014 COCO dataset, the Pascal VOC 2007 and 2012 datasets, or my custom dataset of images of oak leaves.